Hello everyone. There has recently been much work on testing deep neural networks. The focus of our work is ensuring that the testing of DNNs is distribution aware. My name is Swarupa Dola. Deep neural networks are being widely deployed in many applications, including safety critical systems. Rigorous testing is needed to ensure that the applications are safe and trustworthy. DNNs train their models on known data. The resulting models are expected to generalize on the data and make accurate predictions during deployment. The DNNs are trained to have high accuracy on the data sampled from the training distribution. However, the accuracy of these networks on samples that are outside the training distribution cannot be guaranteed. We refer to these inputs that don't follow the training distribution as invalid inputs. Here are a few sample inputs from MNIST dataset. These are some of the invalid inputs generated by Deep Concolic. And here we have more invalid inputs from Deep Explore. It is clear that the invalid inputs are very different from the images sampled from the MNIST training dataset. Our work focuses on the effect of the invalid inputs on the DNN testing process and what approach we take to mitigate these problems. Traditional software has input validation logic separate from the functional logic. Invalid inputs exercise the error handling code, while valid inputs exercise the functional logic of the software. This separation of input validation and functional logic is not present in DNNs. This has several effects on the testing process. Recent research on testing DNNs such as Deep Explore do not check the validity of the test inputs that they generate. Our study indicates that they generate a large number of invalid inputs. Also, the various testing techniques measure test coverage based on the number of neurons activated. However, the same code will be exercised for both valid and invalid inputs. In other words, there will be some overlap in the neurons activated for valid and invalid inputs. In such case, invalid inputs can inflate the test coverage. Not distinguishing between valid and invalid test inputs presents some problems. A testing technique that generates a large number of invalid inputs adds little value to testing while increasing the testing cost. Invalid inputs inflate test coverage and thus provide a false notion of test adequacy to the developer. And when the number of invalid inputs is very large, they waste developers' debugging effort. In the rest of the talk, I'll present some of the challenges of invalid inputs. First, I will talk about the invalid inputs generated by recent DNN testing techniques and their effect on the coverage criteria. Then I will present a method to incorporate the notion of the valid input space of a DNN into the test generation process. Through our experimental evaluation, we demonstrated that our technique is effective in generating valid inputs and it improved the neuron coverage for the valid tests. I'll finish with an experimental study to answer various questions about valid invalid inputs and the coverage. The first research question that we studied is whether existing test generation techniques produce invalid inputs. This diagram presents the input validation logic that we use to classify the inputs generated by the DNN testing techniques as valid or invalid. The generated tests are validated by a deep generative model-based input validator, which classifies the test inputs as valid or invalid. That is, whether the test inputs follow the distribution of the training data or they are out of distribution inputs. There are several methods for detecting out of distribution invalid inputs. Out of distribution input detection is being actively researched by the machine learning community. The approaches can be categorized into supervised, unsupervised, and semi-supervised. We used a variational autoencoder based unsupervised approach for this work. So a VAE based input validation is used for the input validator module, and we studied three testing frameworks: Deep Explore, DLFuzz, and Deep Concolic. We conducted the experiments for 2 datasets and 8 network architectures. We found that all the 3 testing techniques generate a significant number of invalid inputs. 42% of the generated tests are classified as invalid on an average, and 73 to 100% are invalid in the worst case. So how do the invalid inputs affect coverage metrics? We use a VIE-based input validator, and we use deep explore, DLFuzz, and deep concolic for test generation. The input classification logic is extended to show the metrics used for measuring the coverage. We apply neuron coverage and extended neuron coverage metrics, including K multisection neuron coverage, neuron boundary coverage, and strong neuron activation coverage. We computed the coverage metrics for both valid and invalid test inputs generated by the testing techniques. Through our experimentation, we found that invalid inputs yield high coverage for a variety of coverage criterion when compared to valid inputs. The overall coverage is frequently increased by the invalid inputs, increasing it beyond what could be achieved by the valid inputs alone. We next developed a technique for incorporating an explicit model of the valid input space of a DNN into the test generation process. The next research question relates to incorporating VAE into the test generation and its effectiveness and overhead. Here is a diagram representing our approach to test generation. The valid input space is modeled by the deep generative model in the diagram. We use a variational autoencoder as the deep generative model in our experiments. It outputs the reconstruction probability of the test inputs. We use two objective functions. One is the reconstruction probability of the test inputs. Other is the gradient descent-based test generation techniques objective function. Multiple objectives are solved using gradient descent to generate valid test inputs. We use deep explore as the baseline test generation technique in our evaluation. So the objective now becomes neuron coverage plus goal to make the model mispredict plus the probability density output of the variational autoencoder. The experimental results of our study demonstrate that incorporating a VAE into the test generation eliminates the generation of invalid test inputs. It significantly increases the generation of valid inputs, reduces the time to generate valid tests, and increases the coverage achieved on the generated valid test inputs. So VAE detected a number of invalid inputs in the test generation techniques that we explored. Is this true for other generative models? Here is the setup where instead of a VAE, we use another generative model, Pixel CNN++. The probability density output of the Pixel CNN++ is used to classify the test inputs as valid or invalid. The results follow the same trend as observed by the VAE-based classifier. However, the percentage of test inputs classified as invalid by Pixel CNN++ and VAE-based classifiers are different. So invalid test cases are identified with different OOD detection techniques, but the number of invalid tests is sensitive to the deep generative model used. In summary, we show that the existing DNN test generation techniques do not distinguish between valid and invalid inputs. They generate significant number of invalid inputs which affect the coverage and the time to generate valid test inputs. We developed a test generation technique that embeds a generative model to generate valid test inputs. This technique is effective in eliminating invalid test inputs, increases the number of valid inputs generated, and also improves the coverage achieved by the valid tests. Invalid input detection is sensitive to the architecture of the generative model used. We plan to explore using other out-of-distribution input detection models for DNN testing in future. Please refer to our paper for detailed results, and our implementation is available in GitHub and it is open sourced. Thank you.
Hello again. Welcome to the live Q&A session of the third paper for deep neural network session. The paper is distribution-aware testing of neural networks using generative models, and Swarupa is here as the leading author to answer your questions. Please go ahead and write your questions to the chat. We will be very happy to discuss further. While waiting, okay, I don't have to wait, so a question comes up. From Hridesh again, thank you. Thank you for the great talk. Could some of your techniques be used to craft input validators for neural networks?
Thank you for the question. Definitely, yes. The input validation module that we used, it could be used in deployment as well to identify the invalid inputs. Also, there are other approaches we can use for detecting the invalid inputs, which uh, we plan to extend our work in future to use those models for input validation. So yes.
Mhm. Thank you very much. I would like to continue with a question while waiting. So, in your presentation, also, you mentioned that the result is also depending on the generative models you use. And so, do you plan to work on these generative models in your future research? And is there a way to kind of decide what kind of generative model should be used in with different kinds of deep neural networks?
Yes, so we used generative models in our work, but there are other approaches for detecting invalid inputs. Like few approaches use softmax scores um,
Mm,
to detect the approach. Few use training separate classification models for detecting
mhm,
the invalid inputs. And what we believe is that every model has pros and cons. So we believe like we could come up with some hybrid approach where we can use these models and come up with a improvised input validator.
mhm. And so, do you think like is there a way to decide which one to use, or in which case an ensemble or a hybrid version would be? So, can you guess based on the data distribution? What do you think?
So it is challenging because we don't have access to the ground truth generative factors. So, but right now, at least for the models and data sets that we used in the paper, they have good out of distribution detection capabilities. However, for real world data sets, much more research is needed to understand how to draw the boundary or
Mhm.
how to use these models in hybrid approach. So more research
Mhm.
is needed there.
Okay. Um, okay, we are waiting for more questions. If you have any, please don't hesitate to write to the chat. I can continue with another question. So my question is about the criteria for using to evaluate the test effectiveness. Uh, in normal systems, we use these coverage values to understand, or we use this again in the first talk. I was mentioning this mutation score values to evaluate somehow the test effectiveness. But in this deep neural networks or neural networks, accuracy or the way to evaluate test effectiveness is a bit more challenging. Do you plan to work on this aspect as well? Like, what kind of criteria should we look at to understand the effectiveness of our approach?
Sure. So the challenge here is with the existing criteria, as we showed in our paper, they fail to
Mm,
distinguish between valid and invalid. So
mhm,
we believe that using more valid inputs is a proper way to measure the effectiveness of the network with respect to
mhm,
the test accuracy. So yeah, we plan to work on developing metrics that are more distribution aware.
mhm. Okay. Um, Also, a new question from Ranjit. Um, thank you for the wonderful talk and Q&A. While removing the invalid input from the test increases the coverage, do they have any effect on the performance of the model?
So we are so the original accuracy of the model wouldn't change unless you retrain. So whatever test inputs the testing techniques generate, there to assess the corner cases or where the model fails. So by removing the invalid inputs, I don't think it'll affect the model accuracy, because what we expect in deployment are the test inputs that are similar to the training data or that follow the distribution. So in case there are any invalid inputs, we believe they should be handled by the um, error handling mechanism of the system.
Okay, so we answered that question, I hope. So what do you think about the size of the inputs in order to decide whether a model performs successfully or not? For example, in your case, it is more towards increasing the valid inputs, but there should also be some invalid inputs. So how do you define that space, or where do you decide how to stop producing more valid or invalid inputs?
So I think coverage criteria plays an important role here. So as I
Yeah.
mentioned, like if we can come up with a distribution aware coverage, and if we are able to measure adequacy over the whole distribution of the training data, and if the model is accurate, if the model meets the like a specific accuracy criterion, I think that's where we can stop testing.
Yeah, so definitely we need a distribution aware coverage criteria. Otherwise, it would be easily biased with the invalid cases because it will just increase the coverage so quickly, right?
Yes, yeah.
With just a single input.
Mhm.
Okay, thank you very much. Do we have any other questions from the audience, or if not, we can actually finalize the Q&A here, and then later you can move to the discussion room and hear or discuss more on your paper with the attendees who are interested to talk more. Thank you very much. I personally liked reading your paper a lot and watching your slides. So thank you for attending. Also to the attendees, thank you for your questions. So hope to see you soon.
Thank you so much.
Thank you.